All right, let's go ahead and take a look at some of the information necessary to complete Lab 10. So the link should be provided and easy to find in multiple places in the lab folder on the quiz itself. Once you get there, you're given several different options, and we're going to use the intro section. Then a couple of things that we need to do before we get too far into it. We want to turn on the natural length and the equilibrium position. So natural length is the spring when there's nothing on it, and then the equilibrium position is where the spring stops when you put more mass on it. So if I come and I put this one on there, then that shows me where it would stop once it settled down. Now, this is pretending that there is no gravity. See, it says damping equals 0, so that's technically going to bounce forever, but we can use the stop sign and make it stop in place. Okay, so then we can see where it hangs. If you've done the pre-lab, then some of this is going to be review. Then if not, then hopefully we'll be able to catch on from what we're about to do here. Okay, so first thing I want to do is I want to find the spring constant for the spring on a particular setting. And in order to do that, I need to know the force that's pulling on the spring, which is going to come from the actual weight of this mass. And you do need to pay attention and remember that these are different words. So a weight has to be something in either newtons or pounds. And considering that our textbook pretends that the standard system doesn't exist, then that means that we're looking for newtons. Grams and kilograms can never be weight. They do different things. They have a different definition. They are not the same. So first, we're going to need to take 250 grams and we're going to need to convert that into newtons to actually make force. So typically we'd go from grams to kilograms, which would mean that we would take our grams number, set it up in a fraction, eventually divide by 1,000. And then once we have that mass, we're going to multiply by 9.8 for what Earth gravity is supposed to be. If you follow through those steps properly, then you should get a converted mass of 0.250 kilograms, and then eventually a weight in 2.45 newtons. Okay, then for this particular trial, we want to be on the first little mark here, and ruler slightly misaligned. I think it's about as close as I can get it. But we want to use this position and we want to figure out what the spring constant must be. Okay, so we have the force. It's the first part of Hooke's law. Now we need to find the change in length. So if we look, the ruler lines up with the original position, the natural length of the spring when there's nothing on it. Then we made it longer by putting force on there. And then we can see the green line for the equilibrium position. It's right around 61 centimeters. Okay, so then because spring constants are typically in newtons and meters, then we want to convert this. So we'll take 61 centimeters, divide by 100, and because the metric system is really nice, we get 0.61 meters, so a number that looks familiar. Okay, then those are the things that we're going to want to put together to find the spring constant. So spring constant K, again, is from the force pulling on the spring divided by the change in length that it causes. So we had a force of 2.45 newtons. That comes from converting the 250 grams through a couple of steps to get to here. And then we have the change in length x of 0.61 meters. If we divide these out, then that's going to tell us that we have a spring constant, a K value of a little over 4. The units in this case, and most often, are basically just sort of collected together. So newtons divided by meters is just going to be newtons divided by meters. Okay, so that's simple enough. If you did the pre-lab, you should have done that before. We saw another variation of this formula several weeks ago in lecture as well. So this, again, should be relatively familiar. What's going to be new, though, is that we want to use oscillations and something called simple harmonic motion to work backwards and see if we can get the same value. So we have this formula from the first page of the lab where we're going to try to do this a different way and see if we can come up with the same answer. And from that formula, there's a particular constant that we need to sort of build up with the mass that we're looking at. Part of that formula, just the numerator of it, deals with 4 pi squared, so it comes from 2 pi where it gets squared, so 2 turns to 4. Pi times pi is just pi squared because it's already an ugly enough number. And then we multiply by the mass that's associated. Okay, so running this through and looking at our numbers, this is 4, and then pi squared, depending on your calculator, it might be easier to just do pi times pi. And then multiplied by our mass is 0.250 kilograms. So the units are important here. Grams are still not going to be useful for us. So we have to make sure we do that conversion like we talked about from earlier. Okay, and then that's going to give us our constant here, 9.8696 kilograms. Okay, and then that's a number. It's going to be very important. We're going to use this several times, so we need to remember that number. Okay, then for the next part, unfortunately, this isn't super exciting, but we want to start this in motion. So it doesn't really matter how much you move it. We just want to make it move. And then we want to use the timer to see 10 oscillations. Just because it's really hard to start and stop for one oscillation evenly. Then also it's a little bit difficult sometimes to tell where to stop and start. So probably pick something like the very top of the cycle, the very bottom of the cycle. It's typically a bad idea to see when it passes through the middle. Also, because it technically passes through the middle twice during its pattern, it's a little bit easier to miscount when you're trying to use the middle. So I'm going to use just the top. And then it's going to be super boring, but we're going to count 10 times and see how long it takes to move. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So we had a time of about 15.66 seconds, and that's going to vary slightly between different trials. So the one that I had prepared from earlier was just a tiny, tiny bit less than the one we got just now, but these numbers are very, very close. Then what we need to remember is that this was the time for 10 oscillations, and I want to know the time for just one oscillation, one path down and back up again for how the mass cycles when it's hanging on the spring. So I think it should hopefully be obvious, but if I want to turn this into the time for one oscillation, just the regular time, that I would need to take this number that I have and divide it by 10. And so because 10 is a number that's counted, we don't worry about significant digits or anything here. We're just dividing this by 10 and writing down whatever we see. So 1.566 seconds. Okay, and then because of the way that the formula works, again, this is one of the formulas from the front page of the lab, but I don't need t on its own. I actually need t squared. So that should make sense if you really stop and think about it, because newtons involve meters per second squared when we're talking about gravity. So, we've got regular seconds in this. It means we don't technically have everything we need yet. So we want to get to t squared, which means that this is 1.566 seconds squared. And then if I run that through a calculator, I'm going to get something around 2.4524 seconds squared. Okay, and then finally, I can use that to find a spring constant, which I know we already found, but we're going to find it through a different method here. And then after all this work, I really hope it matches. So taking these two values and dividing them out, we get 9.8696 kilograms divided by 2.4524 seconds squared. And then plus or minus a little bit of rounding comes out to 4.02, and then the units go to kilograms per second squared. So the number matches 4.02 compared to 4.02. That's great news. But it looks kind of weird when we look at the units here. So, at face value, it would seem like they would be the same because, like we said, the numbers matched. But then how do we know if newtons per meter really turn into that thing? Well, let's try it and see. So newtons over meters. Remember that newtons are already a combination of stuff. So newtons are kilograms times meters over second squared. And then I'm supposed to take that whole definition and divide by meters. And then I think you can probably see what's going to happen now, because these meters and those meters cancel. And if you look at what's left over, kilograms per second squared is the same here. So technically, that's the simplest way to rate the units, and instead of having terms of combinations of things. But normally the newtons per meter is more useful. It shows how it comes from and leads to forces. Also, there's no exponents involved in that. And so for that reason, a lot of times we see in fact, most of the time, we see newtons per meter, even though technically it can be shown either way. Okay, so now we want to run through a couple of similar trials to this, and we want to see where it's going to go from here. So if I move this to the second mark, I want you to notice a couple of different things. You could hopefully see a change in speed from that. So if you look at this, how this one's moving, then look at how this one's moving. So, clearly they're different. The position is also different. So the green line's a little bit higher up. Both of those things should make sense. The spring is now stronger. In fact, we can even see between the two sides that the coils are thicker in the animation. And so that means that the spring is pulling harder on the mass. And that does two things for us. One, just holds it up a little bit more strongly, and so it doesn't hang down as far. But then also a bigger force is going to tend to lead to a bigger acceleration. And so because this thing's accelerating more quickly up and down, we end up with a smaller amount of time. Okay, so let's run through a similar set of trials. Let's see if we can find spring constants for this new information. All right, and then apparently I can't erase that with my last. There we go. Okay, so we want to run through a similar process again. We want to keep in mind that spring constant, if we're finding it directly through normal methods, you take the force on the spring divided by the change in length, which is in meters, but sorry, I want to use the variable x. Okay, so the good news is we already know that the force on the spring is 2.45 newtons because we're hanging down the same mass that converts into the same newtons as earlier. Then now when I look at the position, the closest one here is roughly at the mark before 50. And again, my ruler may be slightly misaligned, but somewhere around here, you can see it looks like it hits the mark before 50. So as a whole number, that would be 49 centimeters. Then we want to keep in mind how the metric system works. 49 centimeters divided by 100 centimeters per meter means that this is going to work out to be 0.49 meters. Okay, which is perfect. That's exactly enough information to find the spring constant like we would normally do. And so if we run this through, dividing these is going to give us basically right at 5. And then newtons per meter, which remember are also the same as those other weird units, but this will work fine for now. Okay, then to confirm our earlier process, we want to go through the same method. The amount that you move this isn't important. We just want to see, again, the time it takes to do one oscillation. And because it's difficult to measure, we're going to find 10 oscillations and then work backwards from there. Okay, so when it gets to the top, then we'll start the timer. And then we want to make sure 10 full movements, which is why you might have noticed last time I started on 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and this time I actually stopped at exactly the same time as my original notes and trial. So that's good. All right, so my time for 10 oscillations is 14.05 seconds. You may get something very slightly higher or lower, but it should be something close to that. Okay, then working this down to find our useful information, we want to remember that that's the time for 10 oscillations. So we want to find the time for just one oscillation. So it's going to be this thing divided by 10, which I think makes sense. And then because of the particular formula that we're using, we need that time to be squared. So we want to go ahead and calculate that as well. So t squared is going to be the 1.405 seconds squared, which is roughly 1.9740 seconds squared. Then, like before, we can find a spring constant from this. So from our earlier mass constant, we've got 9.8696 kilograms that goes along with the 250 gram mass converted around and using all of our special numbers, and then dividing by our time squared that we calculated, we get, remember, kilograms per second squared, which are equivalent to newtons per meter. We get 4.99979. So really, really close to just 5 newtons per meter, which is great because they match each other. Okay, then let's try it again. I think we've already confirmed this is probably a good process, but never hurts. Plus, we needed to get to a certain number of questions or the points to work out, so there's that too. Okay. We want to go to the fourth mark, so second, third, fourth. So notice again the coils are much thicker than they are on the other one that's only set to 1 mark. Then this is moving faster, and then also doesn't hang down as far as it used to. So let's see what we can do with this. We want to try to find the spring constant using our original manual methods. Remember that that's force divided by change in length. It's the same force that we've already seen a few times because we're using the same mass over and over again. And then this time, looks like green line hits halfway between 30 and 40. So our best guess, because it's really hard to read decimal places on this one, is that's about 35 centimeters. So convert that to meters, and we get 0.35 meters. Okay, then dividing this out is going to give us basically an even 7 newtons per meter. Okay, so I left this thing moving this time because I knew we were going to have to come back and run the stopwatch anyway. Good news is the way these lines are set, we don't have to worry about technically stopping that in the first place. Okay, so we want to run 10 oscillations. Again, we want to find one of the extrema, either the highest or lowest point, and then measure from there. So just to show that it works either way, I'm going to measure from the bottom this time, and then I'm going to start at 0, and then watch it go up and down, and then that's 1, and then so on, so on. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so probably would have been easier if I'd followed the instructions from earlier and put this in slow mode, but obviously it takes a lot longer. So I got 11.93 seconds. On my previous trial, I got 11.87. Those are very, very close. So let's run through this information. It's worked twice already, so I'm really hoping it's going to work one more time. But we want to see if we can find the spring constant using the time. So remembering once more that that's 10 oscillations. So from my earlier sample, 11.87 seconds was 10. Then that means my regular time is going to, suppose I should show my work, divide by 10 and become 1.187 seconds. Okay, then because of how the formula works, I don't really want time, I want time squared. So I'm going to take that value, multiply it by itself, and then the calculator tells me this time that's about 1.4 seconds squared. Okay, then one final time. Hopefully we're going to get about 7 from this, I can find my spring constant by taking my mass constant that's associated, dividing by the square of the time, and really hoping that it works one more time because we're almost done. Okay, so there's my 4 pi squared m constant that we calculated back towards the beginning. Then the square of my time, 1.4090 seconds squared. Remember, the units are a little bit strange, but they are equivalent to newtons per meter. And then running that through a calculator, 7.00468, so on, so on. So really, really close to 7 newtons per meter, just like the other one. And that's it.